years of Navcom technology, where he is a senior research engineer. He has previously worked at Magnavox John Hopkins Applied Physics Laboratory and Boeing, as well as a few years as a consultant. His work emphasis is on high accuracy applications of GPS, global positioning satellites. He has authored and co-authored over 40 papers on navigation topics and 20 papers on relativity topics. He has obtained 25 patents as an inventor or co-inventor. Except for 2, all of these patents relate to GPS. Ron received his BS in Math and Physics in 1962 from Seattle Pacific College. He has served the Institute of Navigation as president and as chair of the Satellite Division. He was in the 1994 recipient of the Satellite Division Kepler Award for sustained and significant contributions to satellite navigation. He has also received the Thurlow Award and is a fellow of the Institute of Navigation. It's a great pleasure to have and bring to the podium a longtime member of the MPA, and he's going to talk about GPS, and believe it or not, maybe relativity isn't being used the way we think it is. So everyone give a warm welcome to Ron Hatch.
Let me turn it up.
We could use a little more. He'll adjust the gain.
Okay. In any case, I'm glad to see all of you here, especially some friends and coworkers, and even my daughter. So, let's get started. I want to talk about using GPS to refute the equivalence principle, and just in case you're not aware, the equivalence principle is what the general relativity theory is based upon. And as you'll see, it has implications to the special theory as well. So with that, let's go. I thought a few quotes here would be nice. It skipped a slide. Well, that's okay.
Oh,
Interesting.
Maybe after.
it's gone.
I had
What about that one?
It's gone. Oh, there it
That's
is.
it. I wanted to show that you can actually simplify Einstein without using equations. But I'm going to use a few equations. I have put a few of Sheldon Harris's slides in my presentation at various spots. Okay. In terms of those quotes, which was, does it switch the slides a little bit?
I'll go a few ahead and you tell me.
Okay.
That was
in
3.
any case, let's
No.
let's go ahead with the outline. I'm going to talk first about the equivalence principle a bit and falling electromagnetic radiation. In the typical book explaining the equivalence, they use frequency and they use falling electromagnetic radiation in a gravity field and in a rocket. I'm going to argue that that doesn't work in the gravity field. And then when I have done that in a paper, I got a refutation from a prominent relativist who said it doesn't need to fall, that in the accelerating rocket acts just like the gravity field. And so then I had to write another paper to refute that because he didn't want me to answer him back. So I wrote another paper for that. With that, let's go on.
Is this the next one?
There's the quotes. Again, we're a different order, but let's look at some of them. The tendency of a group of human beings to quickly come to believe something that its individual members will later see as obviously false is truly amazing. A couple more in Lee Smolin's Trouble with Physics. It's controversy that keeps science alive and keeps it moving. Richard Feynman was quoted by Lee as science is the organized skepticism in the reliability of expert opinion, which is good. I like the last one. It is the glory of God to conceal a thing. It is the glory of kings to search out a matter. A lot of you, I know, are trying to search out matters, if you will. Let's go on. Okay, another little cartoon. He says, if only he could think in abstract terms. He's got 2 apples over 3 pears, etc. We're going to deal with the equivalence principle, and we're first going to look at the definition of it. Then we're going to look at its impact on frequency, which is what they normally use to prove it. We're going to talk about GPS and how it refutes it, and then I'm going to give you what I think is a rather illogical quote from a GPS expert. Okay. The equivalence principle was defined in these two places by Einstein and by Feynman. The assumption of the complete physical equivalence, which is the strong equivalence principle, it's called, of the system of coordinates k with gravitational field and k prime uniformly accelerated, we call the principle equivalence. It's intimately connected with the law of equality between inert and gravitational mass, weak. I think before I'm through, I'm going to argue that both parts of those, the strong and the weak, are both false. Feynman said much the same thing in 6 not so easy pieces. Strictly uniform gravitational field and strictly uniform acceleration. Okay, next. Again, we're missing a slide, but we'll probably see it next. So let's, yeah, here we go.
Okay.
First of all, the gravitational, I think there is fundamental confusion in what you read. They often talk about gravitational acceleration and its effect. Well, it turns out gravitational potential is what causes frequency change and not gravitational acceleration. Similarly, velocity is what causes a frequency change with motion, not acceleration. Okay? The implication is that because a gravitational field reveals a frequency difference between two clocks separated in height, and Pound and Repke did an experiment that proved that with a Mossbauer effect, which some of you saw earlier in a presentation earlier. Two clocks separated in the along acceleration axis of an accelerating rocket must also see a frequency difference. This was claimed true in a real recent article that I cite just because it was real recent and showed the same confusion. Einstein says that frequency increases as the electromagnetic radiation falls, and Feynman says the same thing. I want to show that that doesn't happen. Okay? And here we are. Again, let's go to a different slide. We're back up.
That's going forward.
Let's go back up.
Back one.
Back another
Back
one.
another one. And
Well,
I go back
it's missing it.
another
We'll
one.
go ahead. There's a a slide with Clifford Will that I wanted to show.
Okay, that's
There it is.
maybe-
Got it.
Okay. That was the one logically next. He claimed, I've criticized him extensively in my papers, but at least he had the gumption to ask the question. Does the frequency change in transit, or is it the clock rate which changes the function of gravitational potential? And he says there's no way to tell the difference, that they're equivalent. He then goes on to say, well, we can take a clock, and we can, an atomic clock that's based on how the frequency of the radiation of an atom, and we can take it to a higher gravitational potential, and we can see what happens. And in fact, what happens is when it's higher, it runs faster. But he says you still don't know what happens in real time. And that's kind of rather weak logic, in my opinion.
Let's see what
Let's
is
go on.
our next.
The critical assumption,
Oh,
well,
sorry.
yeah, let's go back to the other slide. Yeah, that one.
This one.
That's the one. The proof that both Einstein and Feynman go through is to say that if we have an atom at floor level, and we carry it up to a second floor or something, and then we let it emit an atom, we put energy into the process as we carry it up, and therefore when we emit the atom back down, it's going to have more energy when it falls, so it's got to increase in frequency to show that increase in energy. That's their argument. And it seems on the face of it, E1 minus E0 being the photon energy, and the energy E0 over C squared GH being the amount of extra energy they had to put in to carry the atom up. So let's go to the next slide again if we can find it. Yeah, here we go.
Oh, was it that?
Yeah, that's the one. The same amount of energy is required to emit, the assumption that they made is that the same amount of energy is required to emit the radiation at each gravitational potential. I say that's not obviously true, show that it is obviously not true. Okay?
Yeah. I'll leave it there.
And here we come to that argument. Start with, first of all, Will, as I already indicated, Clifford Will admits that you can take a clock to higher gravitational potential and see that it runs at a different rate. But to me, right on the face of it, that shows that it's the radiation is more energetic at the higher potential. But in fact, you could take both clocks. Well, that's in fact what he suggested doing. Take one clock up, let it sit there for quite a while, and then take the other one clock up later, and you'll see that there's been a cumulative time difference. The one you took up first ran the fastest, and that pretty much shows that in fact the energy radiated at a higher potential is more energetic. I'm in the last section of the paper, the third major section. I'm going to talk about some of the implications of this, which aren't obvious right at the start. Let's go ahead to the next one. How do I, just to add to the proof and show that GPS proves this, GPS clocks are adjusted to run slower before they are put into orbit because they know they're going to run faster up there. The time difference, there are two kinds of measurements that are made in GPS that's very important. What's called the code or pseudo-range measurements and the carrier phase measurements. The code measurements are a measurement of the difference in time. The time of the satellite is encoded onto the signal and sent to the ground. So by decoding the message, we know when that signal was sent. On the ground, we use the time in the receiver to measure the length of time it took, and that gives us the range. The carrier phase, we undo that code modulation and can recover the carrier phase. The code measurement has one important characteristic. It's an accurate measure of the range except for any clock errors, but also it's much noisier than the phase measurement. So we like to make the carrier phase measurement, which measures the change. By integrating it, I can measure the change in the range. Well, it turns out, because I happen to be the first one to do this, they call it the Hэтch filter, and it's on almost every GPS set. They smooth the pseudo range with the carrier. Now, if the clock didn't increase if the clock didn't run faster at the higher rate, the time measurement would diverge, and you would get a lousy code measurement. Furthermore, it wouldn't agree with the carrier phase measurement, and you couldn't smooth them. So, and we typically, with a dual frequency set, can smooth it for 15 minutes to half an hour to get rid of almost all the code noise and be left with centimeter kinds of noise on the carrier phase. So these measurements are made in real time, and they get rid of that weak logic of Clifford Will to show that, in fact, clocks run faster at higher elevation. They don't gain frequency as they fall. Radiation does not gain in frequency as it falls. Okay, next slide. Double or nothing. I thought this quote out of what's generally called the GPS Bible. Ashby and Spilker, two great big volumes. Parkinson, pretty much the originator, or is called the father of GPS. But he says the only reason I put this first part in is because it said second, but he was saying this all in one paragraph. The light ray seems to have weight and be attracted by gravity. Actually, what happens is the bending is caused by the difference in speed of light. There's no attraction by gravity. Second, the strong equivalence principle implies that light traveling downward in a gravitational field is shifted to a higher frequency, i.e. it is blue shifted and gains energy. And this, as a consequence, atomic clocks at a higher elevation of gravitational field run faster. Now, if my logic is correct, that would double the effect.
Double fast.
But this is the kind of logic you'll often see in a lot of the relativity papers. I think many of you would agree with that. Okay, let's go on. Now I want to talk about a transition. I want to talk about the rocket. Now, by claiming that the clocks run at different rates and there's no energy in falling, I pretty much demolished the argument that an accelerating rocket, you will measure a difference in frequency caused by Doppler. But that's not equivalent, obviously, anymore. They're different phenomena. The clock cumulates, Doppler doesn't cumulate, if you will. So I wanted to address, in a paper I made this argument, and I thought I had put the equivalence principle to bed. But in fact, Brad Parkinson sent my gravity paper to a prominent theorist again, and he came back and he said, I read a little bit of it, I saw an error, and I didn't read any more, and I don't want to hear back. So I wrote another paper addressing his argument, and his argument will come up. He fundamentally claimed that, yeah, okay, in an accelerating rocket, the two clocks will run at different rates, just like the other one. So that's the next argument that I need to address. Next slide, a little bit more on the transition. The original paper I wrote, I argued that the forward clock and the aft clock, because they were in the same accelerating frame, would run at the same rate. Well, it turns out I did make a minor mistake. If there's length contraction, then there's a frequency effect in the fourth order of the inverse C. Rather small, but it'd be easy to take care of with a micrometer or nanometer to spread them apart. But in any case, this led to the claim that infinitesimal Lorentz transformations will cause the clocks to run at different rates. So that's what I address in the next section. Again, he hasn't made any progress with his theories recently, so he's been working on his resemblance to Einstein. I look at authorities, Goldstein, Meisner et al., Mueller, and Ashby, and I talk about several different topics here in trying to prove that infinitesimal Lorentz transformations don't really work the way they think they do. And I'll look at an alternative hypothesis, the clock hypothesis, that's been written up by Professor Goy in Italy. And then I want to look at some clock biases and then compare the two, clock hypothesis, ILT. Look at the Grace satellites, which show a problem. And finally, the solar gravitational effect on clocks. Okay. These are just references to some of the quotes that I will look at. Let's go ahead. Goldstein claims that a particle being accelerated with respect to the laboratory can be linked to the laboratory frame via a Lorentz transformation. The Lorentz transformation instantaneously matches the particle's accelerating frame to a frame moving at a velocity v with respect to the laboratory frame, and thereby gives an instantaneous mapping between the two frames. Turns out that's equivalent to an infinite series of infinitesimal Lorentz transformations. What does that do? The primary thing that does is it keeps the speed of light at c, because the Lorentz transformation was derived as a way to force the speed of light being c in every inertial frame you're working in. He claims it has important applications in atomic physics, and that's primarily based on the Thomas precession effect, which it's used to explain, and we'll look at that briefly. And yeah, okay, that I've already said. Let's go ahead. I think this one may be slightly out of order, but we'll go ahead and address it. The infinitesimal Lorentz transformation causes, when you add two Lorentz transformations that are not in the same line in different directions, it turns out mathematically that causes it to rotate. But people have said, where in the world does the torque come from that causes this thing to rotate? You've made it mathematically rotate. What physically makes it rotate? Mueller wrote a paper that he said, Thomas precession, where is the torque? And then he came up with a way to get some torque. Namely, he showed that if spin does length contraction and inertial mass increase, then that moves the center of mass offset from the center, and that will cause a torque if you're putting the force on the total object in the middle. Well, I think his explanation is pretty close to being exactly the way I would expect it to be, but that would double the effect again if you still claim the mathematics. This mathematics has nothing to do with the Lorentz transformation mathematics. So again, we pick up whatever explanation we think might fit the data and use it. Next slide. The clock hypothesis by Goy, when I first wrote this paper on this, I put Goy in and I put the Lorentz transformation Goldstein statement in, and the first reviewer says, what's the difference? They look the same to me. They aren't really. Here it says that the clock runs at the instantaneous rate. In other words, the clock is driven by velocity and velocity only. And I cite the muon storage ring to show that, in fact, a 10 to the 8th g doesn't affect the frequency of decay of a muon, only its velocity in that ring. So we know, so we're quite sure that the frequency is affected by the velocity and the velocity only, but you can instantaneously adjust to that frequency rate. Okay, again, we're probably a little out of order, but let's go ahead. And now, that's okay. Let's go back to that one. The two versus, the one versus the other, the ILT requires the speed of light is always measured as the isotropic value of c, whereas the other one, the two clocks separating in a long velocity direction, will remain synchronized as the frame is accelerated. This implies a constantly changing clock difference, because that's required if you're going to measure c, which is measured from another standard. The speed of light will not be measured as isotropic value of c unless the clocks are resynchronized if Goy is right with his clock hypothesis. So they're significantly different, and we're going to try to show that, in fact, the implication of Goy is the one that's right. A little bit of bypass, a little bit of mathematics to show that, in fact, in some cases, clock biases are generated naturally. And in fact, here's one. I've got a moving frame v, and then I have a clock that's moving in that frame by a small velocity v. And if I look at the frequency effect, incidentally, that delta f should be delta f over f0. It's the fractional change. What is really critical is this, the two terms on the end, when you square that v plus v, the v squared and the small v squared are easy to explain. The small v squared can become negligible by moving the clock at a real slow rate. So slow clock movement is what people often use to calibrate one clock with another one. The first term, v squared, orbital velocity, affects all clocks on the Earth in the same manner. But the middle term is kind of interesting. It integrates into a clock bias. When I take v as the partial of x with respect to t and integrate that, I get a clock bias term. It turns out, and in fact in one of my early papers I showed this, that clock biases are naturally generated on Earth exactly like this, and this is what makes it look like the speed of light is c on the Earth. But let's go on. The Lorentz transformation is shown here. T transforms and X transforms. I like Sellery's transform, and we'll talk a little more about that. He says, yes, clocks do change, but there's no clock bias term in it. And in fact, he says position changes. It turns out in the forward direction, this is identical with the Lorentz transformation in position. But in the reverse direction, Lorentz puts another gamma. He does a double shortening, whereas Sellery undoes the shortening, which we'll see is a little more logical. In any case, the difference in time, it turns out, is exactly equal to that term, including the velocity of the Earth and the x position in the Earth's frame that we derived from that slide just in front. So there is a clock difference between the Lorentz and the Sellery transformations. That is exactly that clock bias term. Okay? Okay. ILT's, the infinitesimal Lorentz transformation would require a constantly changing clock bias. But we saw that clock bias was a function of velocity and position, not acceleration. And that's why this does not work, and that's why the ILT doesn't work. If you were to resynchronize your clocks, yes, you could measure the speed of light, because Einstein resynchronization, in fact, creates exactly that same clock bias. Okay? Just to give a little evidence for it, the GRACE satellite, Gravity Recovery and Climate Experiment, they put GPS receivers in those two clocks, and they send signals back and forth between them. And it turns out they use the GPS time at transmission, time at receipt. In effect, that's including the Sagnac velocity effect into that. So that if you just looked at the instantaneous difference in the speed of light between them, you'd get C plus V and C minus V. In other words, they keep these clocks synchronized in the non-rotating Earth-centered inertial frame by using GPS to time the signals. And then they use the time of transmission and the time of receipt, not the instantaneous position between the two. Okay? Another effect, the Sagnac effect, which many of you are familiar with. The one-way Sagnac effect is claimed to apply in GPS measurements, and they claim it's the result of the Earth's rotation. I once computed it's something like the curvature on the surface of the Earth is something in the few nanometers. So that much curvature to create a big, huge 29-meter effect at the equator looks like it's stretching things. Let's look at it. Wang, in a very recent, I think 2003, constructed fiber optic gyros and showed that the Sagnac effect still applied without any area in the equation. Virtually all Sagnac equation you'll see includes the area, but if you retranslate that, you can put it in terms of the velocity of the moving fiber and the length of that fiber in the direction of the movement. So he pretty conclusively proved that it's a linear effect and it has nothing to do with rotation. Let's go on. The GPS design document, I just point out that it says the distance has to be expressed as the receipt time, T sub r, minus the transit time of the satellite. So again, it shows the Sagnac effect is present in the design document to get the right answers in GPS. Okay? Here's that equation I was mentioning. Generally, the Sagnac effect, and it's a two-way Sagnac effect. Generally, when they rotate, they send the beam in opposite directions. In GPS, it's one way, and they managed to put it in a form that's pretty close to the original. It's only half as big because it's one way. They said it's 2 times omega over c squared times r sub a times r sub b. Well, r sub a is a vector from the center of the Earth to the receiver, and r sub b is the vector of the satellite signal path. And it turns out that's the area of that triangle that gets swept out as the signal moves from the satellite to the receiver. But Wang and al. proved that it was better written, the general case that applies not only when it's circular but when it includes no area, is that it's twice the velocity times the length over c squared. I can take the GPS form and put it into a form where I call the velocity of the receiver times the receiver's position in the along track velocity direction divided by c squared minus the velocity of the receiver again at the satellite position in the along track velocity direction over c squared. But then I could cancel that out by putting clock bias, so minus v over vxr over c squared, which is exactly the clock bias that we showed difference between Lorentz and Celery transformations. Now, we can't do that for all these receivers because they're all spinning in a different direction. So I can't put a clock bias in the satellite that will account for that. So we have to do a Sagnac correction in our navigation. But I can do that for the orbit because the orbital velocity is the same at all receivers. So let's go ahead. Okay, next claim. Ashby again, in what's generally referred to as the GPS Bible, claims that the sun's gravitational field is canceled because we're in free fall on the Earth. It's free falling towards the sun. Actually, what happens is the sun's gravitational field, the gradient of it, in other words, the difference of the satellite on one side of the Earth and the difference on the satellite clock on the other side of the Earth, is just enough different that if you integrate that till halfway or quarter way around the orbit, actually it's the whole upper half and the bottom half. If you integrate that, you change the clock bias exactly the right amount to counteract the fact that I'm not going in a straight line path. my velocity vector, my along track x distance, has changed direction. And it turns out in each case it's the gradient, or the derivative with from the sun, the gradient of that gravitational potential with respect to distance. So the same thing that causes the force to change the direction changes the clocks to change the bias direction, so that it still looks like my clocks still looks like the speed of light is c on the Earth. A neat effect, but they claim it's not even there, and they claim it's not there because of ILTs. Now it turns out, just a little bit more, the spin speed of either the Earth's surface or the GPS satellite also creates a bias, and because it adds in one case the clock goes slower, in one case it go faster, and that also makes sure that as the Earth is spinning, that clock bias is still in the right direction. Beautiful, beautiful design, in my opinion, to make it so it looks like the speed of light is always c on the Earth, and makes it much easier to run experiments. And I call that an amazing result. Clocks appear to be Einstein synchronized on the Earth, but actually what's really happening is you've got a celery transformation with a clock bias. If you undid that clock bias on the Earth, it would look like the speed of light was isotropic with respect to the sun. Okay? Okay. Couple papers that say here's how to go between the sun's frame and the Earth's frame. Use a Lorentz transformation. Actually, they don't use a Lorentz transformation. It won't work. But they do map the clocks across without a bias term. But that's got a problem. Let's look at that problem. That claim to do it the way they do it would actually cause the physical clocks would have to run at two different rates. One rate for the Earth and one rate for the sun. So if the gravitational potential doesn't do what I just said it does, if the ILTs really canceled out that gravitational effect, then we'd have to have clocks running at two different rates in two different frames. I say that that's rather illogical. You could, in fact, perhaps do something like that if it weren't cyclical, but a cyclic difference just cannot occur in two clocks running at the same rate. Okay? Another interesting thing that turns out, I assume pretty much all of us, I think, agree that a clock runs slower when it's moving faster. But a lot of people seem to question the length contraction effect. Well, if mass increases with velocity, which I think most people agree with, the inertial mass increases with velocity, then it turns out, just like that clock effect, when the speed adds, my inertial mass has increased, and if the conservation of momentum is to apply, that means I go a little bit slower on the top. It means I go a little bit faster on the bottom, but the Earth keeps moving at the same rate, so I get some length contraction in the orbit. Now it amounts to 10 centimeters, roughly, at GPS orbital height, so it's not very big. In fact, it could be lost in the noise of the measurements in most cases. But nevertheless, it's theoretically there, and if you believe in mass increase with velocity, you've got to believe in length contraction. Now, it turns out, because that helps map the speed of light to c in the two frames, it's completely invisible to the normal way we measure it. But I believe VLBI, they're talking about putting VLBI on the moon, and that's a large enough distance that you'll get something like 1.5 meters of length orbit contraction. And I think if you use that to measure the direction of stars, you'll start to see a length contraction measurement for the very first time. It turns out it's an extremely hard thing to measure because it's compensated for with other facts. Okay. Just a little bit more about this Earth effect. I claim that if we, for example, if we use the sun as the reference frame up there, because of Earth's movement and clock slowing and length contraction, we get a moving frame. Now, if you add a clock bias, you'll get what looks like a Lorentz transformation. In other words, the speed of light does look like it's c. Now, it turns out, if you go through the math carefully, it's scale different. The speed of light is gamma squared slower in the Earth's frame than it would have been in the sun's frame. And there are some other effects that one needs to watch out for. But that scaling effect is ignored, and that's why when you do the reverse process, you have to go back that reverse way. In order to show that momentum and energy are conserved, you have to remove the clock bias. Then you can see that they're conserved, and then you can transform back to the sun. So it goes in the opposite fashion, and a Lorentz transformation per se will not really work. It's scaled wrong for one thing. Okay. I have suggested the experiment in one of the papers in which I use the Mossbauer effect, namely the same thing that measures that free fall, to say that ILTs do not work. They claim that the Earth falling cancels the effect. Well, if I had a falling Mossbauer experiment, just like they did at Harvard, where they measured the change in frequency, I claim in fall they would still measure it, whereas what they're claiming is that that acceleration of the fall cancels it out. I don't know how expensive this would be to do, but it's an experiment I'm plugging, and I'm hoping that someday we'll get to do. Okay, next. Finally, we're ready for the next section. This cartoon incidentally says, aha, just as I expected, aha, just as I expected, aha, just as I expected, boom. So some things we don't expect. We're talking about the conservation of energy, gravitational potential effect, and some velocity effect in turn, an unusual velocity effect in my estimation. Okay? I say there's some huge implications of that first thing we derived, namely that the energy, radiant energy, does not increase when it's falling. And one of the things that says is gravity doesn't act on electromagnetic radiation. And that's a huge problem. In fact, I think it's Davies in one of his books claims that this is the biggest problem in physics, that the energy of the vacuum is on the order of 10 to the 120th, and yet they can't see any effect of it due to mass change or curvature, etc. And this kind of solves that problem because it says electromagnetic energy is not acted on by gravity directly. And I say if the energy level of electrons changes with potential, then I think the rest mass energy must change with gravitational potential as well. And that implies that gravity doesn't supply any energy at all. It simply converts the rest mass energy into kinetic energy when it falls. Among other things, that says kinetic energy can't be acted on by gravity because it would be trying to convert kinetic energy to kinetic energy. So let's go on. A little bit about that, not nearly the detail I'd like to go into, but if gravitational energy comes from the rest mass energy, then the spatial gradient of that gravitational energy should give me the gravitational force. Well, up in the top row equation, you see the scale factor for gravity that Einstein used in his developments. You see another one that's often used that's called the isotropic scale factor, and they're different. The second one is the one that I would use, I think, almost immaterial to this. I believe in a solid ether that's compressed, if you will. And the way pressure would relax would be exponentially. So that's another argument for this one. Well, they're different in their third order terms, second order power of GM. And if you take that gradient, where I say the total energy is mc squared times s, incidentally, then when you take that derivative, you get the bottom equation, the force, and that s stays in the top. In other words, some of the energy is canceled out when you fall. There's less energy in the total system, and that's the defect energy. In other words, just like an electron in an orbit around an atom there's been some energy gained by going to that orbit. Same way, this would argue that when you drop an orbit, there's less energy total available. Well, it turns out if you take Einstein's scale factor and take that same derivative, the s winds up in the denominator, saying that the force gets stronger instead of weaker. But if the force gets weaker, like we claim, you automatically have no black holes because it gets weaker and weaker as the gravity gets stronger and stronger. I don't think I put it in here, but it also explains the anomalous redshift that you see from some of the blue stars. that have never been explained. And Art, in one of his books, Seeing Red, talks about that mismatch some. So let's go on. Implications continued. Back up one, I think. Yeah, this one. Oh yes, conservation of energy, or no, I'm sorry, right here, the weak equivalence principle. Does the inertial mass and the gravitational mass say the same? Well, it turns out if you look at the kinetic energy, well, if I let a clock, if I lower it in the gravitational potential, it slows down, has less energy. When I speed up, give it more kinetic energy, it also slows down. I claim that has to be the same phenomenon. Namely, the structural energy is decreasing as you speed it up. That means its kinetic energy is actually doubled. So instead of 1/2 mv squared, I'm getting mv squared. It's a hidden component of the kinetic energy. But the fact that it radiates at a lower frequency would argue pretty conclusively that that's there. And in fact, forget the S here. What that says is the total energy is the inertial mass times the speed of light squared, at a given, if I hold S the same at a given gravitational potential, then the gravitational mass or structural mass has decreased by gamma, and the inertial mass again has increased by gamma, and I get that equation, which in fact shows a mathematical equality. Next. I found an interesting example that tends to support that. And incidentally, there have been a few papers published on temperature of electromagnetic radiation showing a similar effect. But this one is the simplest one that I've been able to come across. If I take a pendulum in a gravitational field and I move it sideways in that gravitational field, so that I don't change the gravitational field at all. Now, admittedly, this is a theoretical experiment. I can't really do it accurately enough. But the equation for the pendulum has the square root of the gravitational mass in the numerator because of the force, gravity force, and it has the inertial mass in the denominator, square root of that, because of the pendulum weight. And it turns out, unless they change differently, that clock is going to run at the same rate, and I could compare it to an atomic clock, and I could measure my velocity. Well, that's rather illogically. It'd be the first thing that we've ever come across that we can measure our velocity with. So I claim that the pendulum is a pretty good proof that in fact there is a divergence between the gravitational mass and the inertial mass, and it is real and will show up. Okay, next. Just because this defeats the weak equivalence principle, and there are all kinds of experiments that claim the weak equivalence is proven to 20 decimal places or whatever, I thought it would be worth all the tests that I've ever come across just measure equal rates of fall. Well, if they're both changing the same way in all mass, then that wouldn't measure any divergence at all. The only way you're going to measure a divergence is actually comparing stop to moving. There's later indications that it's also the case, but I wanted to point that out. They prove it by saying mass falls at the same rate. That's not really a proof. Okay? Okay, now conservation of energy, which is even more interesting. Special relativity claims that the inertial mass is conserved. In that first equation, they say the inertial rest mass energy squared is equal to the total energy squared minus the inertial mass times the velocity, namely the momentum, times c squared. Well, I claim that's a good equation in a given system, but it doesn't work from one frame to another. And here's why. If I divide E solve for E, divide through by E, namely m sub I c squared, then I get m0 squared over m psi squared, which turns out to decrease the equivalent mass, and I can replace it with m sub g. So I get that same equation that I derived from the frequency results earlier. And now, what would you expect to be conserved? If I'm on the Earth and I change from a sun's frame to an Earth frame, what I'd expect to be conserved is the total energy minus the kinetic energy of the Earth. And if we plug that in and look at it, lo and behold, we get the gravitational mass times c squared. So if I rescale the rest mass by gamma, then indeed that equation would work. But just like the total Lorentz transformation, there's a scaling error. And they've ignored that scaling error in their equation. I like to see the energy conserved, and special relativity by itself doesn't conserve energy. Okay? All right, we're nearing the end here, I think. What are the actual apparent, equivalences? First of all, the effects are energy, they're not acceleration. Gravitational potential affects the radiated frequency because the gravitational potential energy is proportional to the rest mass energy. Speed of movement with respect to an absolute frame drives the radiated frequency because, again, the structural mass energy decreases as a function of that speed. The inertial mass increases as the speed with respect to the absolute rest frame increases. Structural mass decreases as the speed with respect to the absolute rest frame increases. Longitudinal length decreases as speed with respect to the absolute rest frame increases. Again, momentum, especially spinning bodies that are moving, would have to contract in length. I tend to think that particles are spinning standing waves, which would lead to the length contraction directly. As a result of those coherent physical changes, I would claim that we do have two equivalence principles. With absolute speed, all local physical experiments will yield results that are independent of the speed given the same gravitational potential. Note the word local. When you get something from outside your local frame, you can measure some of these effects. With gravitational potential, all local physical experiments that do not involve gravitational effects will yield results that are independent of the gravitational potential. Okay? These are just some of the references. I think 4 papers here that all but one of them are in physics essays, but you can get more detail on my arguments in those papers. Next, Craig. Finally, this cartoon was titled, as I mentioned next week in my talk on reversible time. So I thought I ought to look a little bit at what's next. Some unexplained phenomena that I'm having fun doing some work on. First, there's the pioneer effect that I think some of you are aware of. It turns out there's an anomalous Earth gravity assist. When they send satellites past the Earth to speed them up, it turns out they get a velocity towards the South Pole that they can't explain. There's also some strange stuff going on measuring the gravitational harmonics of the Earth. I think those may be related. There's an apparent relativity of gravitational electromagnetic forces on the Earth. Fortunately, I'm trying to go through and derive exactly how that happens. I'm most of the way there on that one, but haven't finished the paper. And finally, one I just became aware of, the spin axis translational velocity, there's a kick in millisecond pulsars that they don't understand. Almost all of them are going at a higher speed than they expect them to be translationally, and it's in the direction of their spin axis. And I think that's a pretty interesting phenomenon as well. So let's look at a few more. The pioneer effect I did write a paper on, and I believe in expansion, Hubble expansion. I knew a lot of people don't, but it turns out I wrote a paper using the Hubble expansion to show that if the total universe ether is expanding, it's like a higher gravitational potential, and it exactly explains the pioneer effect. That was in physics essays last year. It's analogous to the Pound-Rebka experiment, and they never did blame Pound-Rebka as being a velocity acceleration. They recognized that it was a clock frequency effect. So there is a clock frequency effect. Okay, satellites with accelerometers are being proposed, which they will launch to measure this momentum and see whether there really is an accelerating force there, or whether it's the phenomena similar to what I claim. Okay. The gravitational harmonics and the Earth gravity assist, it turns out, I think, could be caused by a gravitomagnetic or kinetic field effect. Pretty much all the general relativists believe that there's a gravitomagnetic effect, similar to the magnetic effect, but it's due to moving mass instead of moving charge. It turns out the mathematics is daunting, and I haven't proven this, but I believe that if you have a satellite moving with respect to the cosmic background radiation, it would have gravity and magnetic field. So does the spinning Earth, and that spinning Earth one would be pointed downward pretty much, and would fit the phenomena. There's a millionth the size of the gravitational force directly. That creates a southern velocity. I think it would also explain the phenomena of the anomalous gravitational harmonics. It turns out if they put a satellite in polar orbit, as the Earth spins under it, theoretically it should measure all the gravity field and they should be able to get all the terms. But it won't work except for the satellite that's in polar orbit. They have to put some at other orbits in order to get a gravity field that will work at all inclination angles. And I think, again, there's probably a hidden force, slight, very small, that would tend to make it look like the Earth's center is downward, is a little bit lower, offset from the true center. And that would complicate, it would only be apparent in the gravitational harmonics if you put it at several different angles. So that's my hypothesis only at this point. Next. This one, as I said, I'm working on. I'm pretty close to having a paper ready on that one, I think. Next one. This one I just become aware of, but I'm wondering if when you compact something, it spins faster. I'm wondering if the momentum direction has to be conserved. And I haven't even begun to look at that. But if it does, that could explain a kick when a spinning star collapses to a neutron star. And to conserve the along momentum of that angular momentum, if it's already moving, it would boost that movement. Only hypothesis at this point. That's about it. Okay, thank you. The cartoon says the universe before the Big Bang, actual size. I wanted to mention there's a book called Privileged Physics that I don't know how many of you buy the hypothesis, but he claims the position of the Earth, the authors claim the position of the Earth, where it's located in the galaxy, and a whole bunch of things combined are there to make science easy for humans, and that God designed it that way. All right? I don't know about that, but boy, when I look at the way the speed of light looks like it's c on the Earth, and all the things that have to work together to make that happen, I think it was probably designed by God for ease of scientific learning. Okay. That's it.
Thank you. We've got a few minutes for questions. If you would be so good, please come up front so we use this microphone where we record your questions. So anyone, we got a few minutes. For Ron Hэтч? No?
Oh, well,
okay, fine.
Ron, that's a lot of information. I was not able to take notes, and so I'm wondering, is this presentation you gave us accessible?
I believe it'll be accessible through the NPA.
This is being recorded, yes.
Okay. Oh, okay. Well, no, I mean the slides.
Yeah, we can post it on his profile. Sure.
Okay. Well, that's good. Then other questions will come out of reading those.
Okay.
Any other questions?
Oh yeah, wait.
If your premise at the end or conclusion, designed by God for the ease of scientific learning, is true, why is it that your presentation is not that easy to understand?
Because I'm trying to search out the underlying stuff to make it easy. In other words, Maxwell's equations actually are a little tough for a lot of people, but at least they don't have to deal with the velocity, the Earth's velocity of what, 326 kilometers per second with respect to the cosmic background radiation.
Ron, I know the author of that book.
Yeah, do you?
He's Cuban.
Yes, right. Yes, yeah.
Okay, Russ?
Are you familiar with the Bergman-Lucas spinning ring model, the atom?
Yes, a little bit. I haven't studied it at length.
Okay, they have shown mathematically, from their paradigm that gravity is an electromagnetic force. And I see you've kind of been touching on that. Is that something you are looking into?
No, I believe actually just the opposite. I believe that gravity is a condensation or a compression of the ether, and kinetic energy is shear energy, and the electromagnetic stuff, electric charge, I believe, is an oscillation of the gravity field, and magnetic is an oscillation of the shear field. And when you look at the equations, I think that explains why some large gravitational phenomena, like earthquakes, are sometimes accompanied. Shaking Earth would create an electric field, and you see that. And I think in the case of one of Jupiter's moons, one orbiting around the other, and you get electric discharge between them, that I think could be explained. The magnetic field of the Earth I looked at one point in time, and it seems to be influenced by the moon with the spin underneath it. So there's, I think, quite a bit of evidence to show just the opposite, that the electric field is kind of a derivative of the gravity field.
I read many years ago the famous article you wrote concerning the Sanya correction, and noticed briefly a brief reference to a 2010 paper where you're attempting to establish a GPS coordinated for the solar system. And correct me if I'm wrong, but wasn't it the really radical aspect of that earlier paper was that you said that the reference, that the receiver could be moved around as much as possible. Well, how can we actually trust any shift of that frame to the solar barycenter if we don't have a receiver there to verify that our...
I'm not sure I know how to answer your question, but I think the measurements, what I'm claiming in the paper is that the very same measurements, if you adjust them for motion and for gravitational potential, and for the celery transformation, you will wind up being able to use them in the solar frame.
Okay, I'll talk to you too after.
Okay.
Thank you.
Ron, a couple questions, or one comment is that I think this, when you said that you don't see any interaction between gravity and light, you said that, right? Or
not quick. There's no direct action.
Direct action.
It causes the speed of light to slow, and wavelengths to decrease. Frequency stays the same, but that change with frequency or change with speed will cause it to curve, as if it's being attracted, but it's not being attracted. Was the point I was trying to make.
Okay. And the other one is you're obviously working in a field. You're very well known for making the I mean, your job is to make this more accurate and more accurate. Obviously, I can see from your talk how GPS constantly seems to be trying to find another almost anomalous thing to try to make it more accurate. Now, you being, I guess you're somewhat isolated in the sense that your colleagues are not out there saying that Einstein's wrong and things like that.
They don't care.
Yeah, I mean, they don't. I guess the people in Vest don't care if you're making a bet. But how is that working in your world?
Well, to some extent, because I've contributed in other areas, people tend to take my word a little more than others. For example, Brad Parkinson liked my gravity paper, sent it on to this relativist, and he wouldn't have done that for an average person probably. So the founder fundamentally of GPS is open to my ideas a little bit. Now he's not a relative. He's not a. He's an engineer.
He has his limits.
Any other questions? Russ, no?
I wondered if you can answer the original eclipse, solar eclipse 1919, that supposedly Eddington said disproved relativity was true. I understand the research I've done shows that either it was totally inconclusive or in fact it proved just the opposite.
I have read analysis of it saying that the data certainly was not conclusive at all. I don't, and that's, people tend to try to prove the existing, what's the right word, paradigm, and that's what I think they were doing. On the other hand, I do believe, for example, the Shapiro measurement of the slowing of the speed of light as it comes next to the sun. Some people have claimed ions would slow it enough. I don't believe that, because it fits a pattern perfectly of the square of the speed of light, the scale factor squared, affecting the speed of light as a gravitational field. So I believe that happens. and that is enough to cause the total bending that Einstein predicted, but not due to the fact that the light is attracted by gravity. It's due to the fact of the speed. And it's often said that the Shapiro phenomena was not foreseen by Einstein. So, phenomena causing it, but he had the phenomena right, I think.
You got a question, Scott?
I do.
Okay.
I'm trying to understand, so if this bending is taking place, is it kind of a density of, you view it as a density of the ether changing?
Yep.
So it's a kind of diffraction thing?
Yes, exactly. Right. That's exactly the way I see it. Yeah.
Okay, thank you.
Yeah.
You understand?
Oh, just one more thought. While I got you.
I got you.
Yeah,
He's got you now.
Do you, you know, there's the 0-point energy paradigm, and you know, from the perspective of your work, you know, there's things like that are measuring differences in the speed of light in Casimir cavities, like the depletion. I guess you would say there's less ether in the way or whatever, but they're saying that they're getting the light from one end of the cavity to the other faster than they should, or sooner than they should, I should say. And do you see that as having an impact on you know, ether theory and gravitational things like Rueda, Puthoff, and
Yeah.
Hage?
In fact, my gravity paper, after I had written it, Hal said, "Hey, I wrote a paper that's almost like that," and he in fact sent me a copy of his paper, and he was right. He had an awful lot of the stuff the same as in my paper. So there's nothing. I think mainly the speed of light measurements that have, some have sped it down, some sped up a bit, and some have slowed it down a bit, but they're using index of refraction phenomena fundamentally to do that, I believe. I don't know how they create a negative index of refraction, but that's what they claim to have done.
Well,
but
we
yeah,
say there's less flux there.
yeah.
Yeah.
In any case, I respect Hal's work for sure. He did it, took a different approach to come up with exactly some of the same phenomena that I do. For example, I get the speed of light squared, decreases with the square as you come down in the gravity field, but the energy comes down as only once as so c squared decreases by a factor of 4 of the scale factor. That means in order for the energy to decrease by only 1, the mass in a gravity field has to increase by the 3rd power, or decrease depending on the direction. And that fits and looks great. And he came up, I think I said in my paper, I haven't ever seen this before, and he showed me a paper he'd written earlier where Hal had derived that same phenomenon based on permittivity and permeability of vacuum.
I'm trying to understand the relationship between the Casimir effect and the van der Waals, because I heard a statement from somebody who said, if you submit a paper to any of the mainstream journals, you know, physics letters and stuff like that, and you use Casimir force in it, it will be rejected. And once it's, even after it's been rejected, replace Casimir force by van der Waals, and it'll be accepted.
I'm not an expert in that field at all, so I wouldn't be able to comment.
Oh, Ron, you invoked the celery transformation. The celery transformation is not a group, therefore it has to decide on a preferred reference frame of 0 velocity. What is that frame?
I believe it's the cosmic background radiation frame, because we can measure velocity with respect to it. Isotropic temperature of the cosmic background defines a rest frame. I think that's probably it. Now, Tom Van Flanderen, the late Tom Van Flanderen, argued that that could be caused by a local, what do I want to say, nova or something that way. I don't know. It turns out that because of this phenomena of being able to map from one to the other, the celery transformation, in one sense, requires you to define which frame you're going to use as a reference. And I don't know any way to get around that. But it seems to be real. Again, the special relativity has a scaling problem when you really look carefully at it. It scales things smaller and then scales them smaller again when you come back. And it's ignored.
You said something earlier about an index of refraction below a negative index. But to me, an index of refraction of faster than speed of light would have to be below the number 1. Was it a negative or less than 1?
Less than 1.
Okay.
I apologize. Yes, I misspoke. Yeah.
Any more? Oh, okay, it's going to be, okay, go ahead, Glenn.
Yeah, my name is Glenn Morford. I have a question, kind of sociological here. The younger Einstein said that space was empty. Perfectly empty, total idealizations, perfectly empty, sort of a positivist approach. And then the elder Einstein of 1920 said you had to have the ether. Now you've dealt with these people that apparently are still using the younger Einstein, right? Because you're the ether guy and they aren't. Can you give us an explanation of why that is?
I think it's what you've grown up with primarily. one of the guys, you know, I don't remember who it was. Somebody said you gotta have to wait till the people trained that way die off. I don't know. But I think I quoted it in my book, which is outdated. But I think it was somebody by the name of Tyndale that said that he can't imagine something oscillating like light without something to oscillate in. So, you know.
You talked about the speed of light changing, and also briefly talked about the Einstein synchronization. I just want to check that it's the use of the Einstein synchronization that makes the speed of light constant, and if you don't use it, then it's variable.
Yeah. Let me clarify that perhaps a little bit. In the longitudinal direction, it takes the resynchronization plus a length contraction. In the offset direction, because it follows a diagonal path, there's no length contraction needed to make it appear that the speed of light is isotropic at a scaled back 1/gamma value.
We done? Okay, we got a lot. Thank you. Ron.